In this lesson, we will learn how to take the derivative of functions that involve products or quotients. We will also learn how to differentiate the four other trig functions. We've only seen sine and cosine so far. And then finally, we will start taking second, third, and fourth derivatives. We begin with the product rule. And what the product rule does is it tells us how to take the derivative, that's what that symbol means, of two functions that are being multiplied together. So for example, like the first thing we see here in example 1a, we have two functions that are being multiplied together. Before, we would have had to FOIL all of this out and then take the derivative term by term. But what the product rule tells us is if you have a function f multiplied by a function g, then your derivative is f prime g plus g prime f. So in this case, we are going to be taking the derivative of the product of two separate functions. And those two separate functions are f equal to 3x minus 2x squared. That's that first factor. And the second factor of g is 5 plus 4x. So now that we have identified both of those factors, f and g, we will now come in and take f prime and take g prime. We'll take the derivative of both of those two factors. Starting with f, the derivative of 3x is 3, constant multiple rule, and then the derivative of x is just 1. To take the derivative of 2x squared, we're going to be using the power rule. We still have that minus sign. The 2 comes down and gets multiplied with the 2 in front. So this exponent came down and got multiplied with that 2 to give us 4. And then the new exponent on x decreases by 1 and is now 1. For g prime, the derivative of 5 is just 0, so I don't have to write that. And the derivative of 4x is 4, because the derivative of x is 1. So now that I have f prime and g prime identified, I can now go back and fill out h prime of x, which is equal to f prime multiplied by g plus g prime multiplied by f. And I'll begin to fill this out. I have my first factor of f prime. That's going to be multiplied by g. And then I have my second factor, my second term of g prime f, which will be 4 times 3x minus 2x squared. Expanding and combining like terms leaves us with this final answer for our derivative. I will point out that for the purpose of WebAssign, I'm pretty sure that it will take simply this answer. And this would earn most credit on a quiz or on a test if I see this in your work. But I am going to be asking that you all simplify your derivatives completely, because as we come to use the derivative to do different things, some of the algebraic techniques that we will do require us to have the derivative simplified. Looking at example 1b, we are again presented with a product. We have two functions being multiplied together. In this case, those two functions are 3x squared and sine x. So I have identified my f and my g for the product rule. I then need to come and calculate f prime and g prime. Both of these derivatives we will be taking using techniques that we learned in the previous lesson. Now that we have all four components, we are able to come and find y prime using the product rule of f prime g plus g prime f. Here we have f prime multiplied by g, and then we will add g prime multiplied by f. And I'm going to choose to write that 3x squared in front of that cosine x. Nothing can be simplified here. We don't have any like terms that we could combine. I will note that it is possible for us to factor out a 3x in this case and be left with this factored version of the answer, but either one of these would be correct. Next, we have the quotient rule that tells us how to take the derivative of a quotient. The quotient rule goes f prime g minus g prime f. Pay attention to that minus sign. And then in the denominator, we have g squared. And of course, we have the condition that the denominator is not allowed to be 0. So looking at example 2a, we're going to begin with the quotient rule by identifying what is f in the numerator and what is g in the denominator. It's important to make sure that you're keeping f to be what is in the numerator and g to be what is in the denominator, because the order in which we divide things does matter. I'm now going to take f prime and g prime. F prime, the derivative of 5x minus 2 is simply 5. And the derivative of x squared plus 1 is 2x. So now we can fill all of this into the quotient rule of f prime g minus g prime f all over g squared. F prime is 5, which we will multiply by g of x squared plus 1, and then we will subtract g prime of 2x, which gets multiplied by f. In the denominator, I will square g. I'm now going to do some algebra and simplify the numerator. Now I'm combining like terms in the numerator to get our final answer for y prime. And there we have our final answer for y prime. In example 3b, we are being asked to find the equation of the tangent line to this function at a particular x value. Now we know that the equation of a tangent line is going to have the form y minus y1 is equal to m times x minus x1. In this case, they have already given us x1. We want to find the equation of this tangent line at x is equal to -1. So I know this is going to be x plus 1 in here once I substitute in -1 for x1. They did not explicitly give us y1, but we could easily find it by plugging x1 into the function. In other words, I'm wondering what is the point on the graph when x is equal to -1. So I'm going to substitute -1 into h, and we get out 0. Now all we are missing is the slope of this tangent line. And to get the slope of the tangent line, we need to calculate the derivative of h and evaluate the derivative at -1. So we are first going to find h prime, and then we are going to plug in x is equal to -1. So to find h prime, we start with our function h of x, which is equal to 1 minus 1 over x squared divided by 3 minus x squared. I'm going to rewrite the numerator so that it is 1 minus x to the -2, and I'll leave the denominator alone. And I did that because to take this derivative, we are going to need to use the quotient rule because this function is a quotient. So the numerator will be our f of 1 minus x to the -2, and the denominator of 3 minus x squared will be our g. We will now calculate f prime and g prime using our basic derivative rules from the previous lesson. So I've used the power rule to take the derivative of f, and I will now simplify that. And I will use the power rule to take the derivative of g. Note that we are also using the constant rule. I'm now going to begin to calculate h prime using the quotient rule of f prime g minus g prime f all over g squared. So plugging in f prime, which is multiplied by g. From that, we subtract g prime, which is multiplied by f. And this is all divided by g squared. At this point, I'm going to resist the urge to simplify this any further because all we really need to know is what is this function equal to? What is this derivative equal to when x is equal to -1? So now I'm going to come in and plug in -1 for all of my x's. Please be careful with the fact that there's some exponents on these x's, particularly when we raise a negative number to an exponent. We need to be very careful with our notation and make sure that we wrap that negative number in parentheses. This gives me -1, and so now I am able to finish writing the equation of this tangent line. I can simplify that because I don't need that -0 on the other side of the equation. If you wanted to take that further into mx plus b form, you could distribute the -1. Now that we have learned the product and quotient rule, we will shift gears to learn the rest of the derivative rules dealing with trigonometric functions. In the previous lesson, we saw that the derivative of cosine is negative sine, and that the derivative of sine is cosine. This lesson adds the derivative rules for the other 4 remaining trigonometric functions. And now we will look at example 3, where we will see 3 different functions and practice taking the derivative of them. In example 3a, our function f is 2 minus sine x minus cosecant x. We're going to come in and we are going to take this derivative term by term. Although it's not necessary to come in and apply this derivative operator to each individual term, I think it will help us see how these derivative rules are being applied, since this is the first time that we are looking at this. Notice that I'm not using product or quotient rule in this example because there is no product and there is no quotient. For the first term, the derivative of 2 is 0. For the second term, the derivative of sine is cosine. And for the third term, the derivative of cosecant x is negative cosecant x cotangent x. Please do notice that I have already brought down the minus sign that was in front of that cosecant x. So this derivative all alone right here will pick up another minus sign. Those 2 minus signs will then combine to give us a positive sign, leaving us with our final answer of negative cosine x plus cosecant x multiplied by cotangent x. I'll start example 3b the same way by taking the derivative of each individual term. Now that I have the derivative operator applied to each term, I can see that there's constants that we can pull out in front of our derivative operator that will only leave us taking the derivative of trigonometric functions. Now we can apply the derivative rules from this lesson. We know now that the derivative of tangent x is secant squared. And we also now know, well, we already knew that the derivative of cosine x is negative sine x. Again, be careful with your signs here because there was already a minus in front of this pi over 2, and then this derivative gave us another minus in front of that sign. So those 2 minuses are going to come together and give us a positive pi over 2 sine x. Our final part from example 3 is asking us to find the derivative of h of x, which the first thing I notice is that this is a product. Yes, there is a trigonometric function in this function, but that trig function is being multiplied by x to the 5th. So we're going to have to use the product rule, which tells us that the derivative of f times g is f prime g plus g prime f. So I'm going to begin by identifying f, the first factor in that product, as x to the 5th, and g, the second factor in that product, as secant x. Now I'm going to use my power rule to take f prime and get 5x to the 4th. And g prime, we just saw up here that the derivative of secant x is secant multiplied by tangent. So our g prime is secant x tangent x. Now we can find h prime of x using the product rule of f prime g plus g prime f. And I'll begin to fill this out. F prime is 5x to the fourth, which is multiplied by g, which is secant x. We will then add g prime, which is secant x tan x. That's going to get multiplied by the x to the fifth. And I'm going to put the x to the fifth in the front. So here we have our final answer for the derivative. I would accept this for full credit. I would like to point out some of the algebraic techniques that we will be doing with derivatives very soon. Notice that I can factor out a GCF here of x to the fourth secant x. That is the greatest common factor between those two terms. And I would be left with 5 plus x tan x. So either one of these would be all right. The second one would be preferred. The final topic that we will discuss in this lesson is higher order derivatives. And this is simply taking the derivative in succession. So for example, we have notation here. If we have a first derivative, we know several ways for us to write that. If I were to take the derivative of the first derivative, that gives us the second derivative, which we denote as y double prime or f double prime. There's also the dy dx notation for that. We continue in that pattern, we could have y triple prime and f triple prime. Once we get past the third derivative, we don't typically write 4 of those apostrophes. We simply wrap the number 4 in parentheses as an exponent to indicate that it is the fourth derivative. In example 4a, we are being asked to find the second derivative of the function h of x is equal to cosecant x. To find the first derivative, which is where we start, I'm going to be using the derivative rule for cosecant x, which is negative cosecant x cotangent x. So now that we have the first derivative, we will need to take the derivative of this in order to get the second derivative. But I can see that this first derivative is a product. We have the first factor of negative cosecant x and the second factor of cotangent x. So I am now going to come in and use the product rule. We have already identified f, and we have also already identified g. We now need f prime and we need g prime. The derivative of cosecant x is negative cosecant x cotangent x. Mind you, we already had a minus sign there. So those two minuses will come together and give us that f prime is simply positive cosecant x cotangent x. For g prime, the derivative of cotangent is negative cosecant squared x. And I know that because this box we have up here tells us that the derivative of cotangent x is negative cosecant squared x. So now that I have f prime and g prime, we are now able to come and find h double prime of x. So to get from this first derivative to that second derivative, we are using the product rule. So we are going to be filling out f prime g plus g prime f. F prime multiplied with g will be a cosecant x and then multiplied by a cotangent squared x. Then we will multiply g prime by f, which will give us a positive, because we have two negatives here, a positive cosecant cubed x. The last thing I will do is I could write this expression by factoring out the GCF of cosecant x and being left with this expression. In example 4b, we want to find the third derivative here. If I were getting started in this problem, I could understand how one may be tempted to use the product rule here because we see this product, but I think it would actually be much simpler for us to just expand the function p of x by distributing this 3x squared. And then we'll simply take the derivative term by term using our basic derivative rules. So starting with the first derivative, we bring down the exponent of 2, multiply it with the 3 to give us a 6. The new exponent on x decreases by 1. Multiply the 3 with the 15 to get 45. New exponent on x decreases by 1. It is now 2. We have our first derivative. Let's continue and take our second derivative. The derivative of 6x is simply 6 because the derivative of x is 1. We'll use the power rule on the second term, multiplying the 2 with the 45 to give us 90. New exponent on x has decreased and is now 1. And then finally, our third derivative, the derivative of 6 is just 0 because it's a constant, and the derivative of negative 90x is negative 90.